Hello viewers, so we have this question that says a 4 kg block is suspended from a spring of constant 500 newtons per meter. A 50 grams bullet traveling at 150 meters per second embeds in the block. So this means to say the bullet gets into the block and is stuck in there. All right. So then A is saying find the amplitude of oscillation. B is saying determine the fraction of the bullet's kinetic energy converted into SHM, which is simple harmonic motion. So the question is under simple harmonic motion and we are told to find the amplitude given the information we have. So let's get the information we have here. We have a 4 kg block. So the mass of block, allow me to represent the mass of block with M and a capital B. So capital B for block. So the mass of block is equal to 4.0 kgs. Then we have a mass of the bullet. Allow me to represent that by a small letter b. So M with the small letter b is for the bullet. So we have a mass of 50 grams. But under here, we use our masses in kgs. So we're going to convert it to kgs by dividing by 1,000. This will give us 0.05 kgs. All right. So we are given, say, the bullet is traveling at a speed. So we'll use VB again, V with the small letter b to mean the speed of bullet. So it's given to be 150 meters per second. But from that, we are given to say we have the spring constant K to be equal to 500 newtons per meter. So this is the information we are given from the question, and the first part is telling us to find the amplitude of oscillation. Now, how do we find the amplitude of oscillation? In order for us to find the amplitude of oscillation, we have a few formulas that can help us find that, but all these formulas will require us to first find the speed of the system. So the speed of the system we're talking about is when the bullet gets into the block, they form one thing and they'll be moving together. So that's the system we are talking about. And this system will be moving at a certain speed. That speed at which this system, which is the bullet embedded into the block, is what we are looking for. So how do we find that? We can find that speed using the law of conservation of momentum, which says the momentum at the beginning must be equal to the momentum at the end. Initial momentum must be equal to the final momentum. We are conserving this momentum. Now, momentum is given by mv, mass multiplied by velocity or speed. So in this case, we are talking about the momentum of the bullet being conserved, also the momentum of the block being conserved. So our formula will be the sum of the momentums that we have at the beginning must be equal to the sum of the momentum that we have at the end. So we'll say we'll have mb, which is mass of block multiplied by the speed of the block added to mass of the bullet multiplied by its speed. This will be equal to the mass of block multiplied by speed of block again. That will be added to the mass of the bullet multiplied by the speed of the bullet. Now let's call this one 1, momentum 1, and let's call this one momentum 2, just to differentiate between the two. So now what we should understand is both the bullet and the block have got masses. But initially, the bullet is moving before the block started moving. So at the beginning here, you find that the block, before it was disturbed by the bullet, it wasn't moving, but it was stationary. Because it was stationary, it implies to say its velocity, since it was stationary, is 0. So now replacing with what we have here, we'll say this expression here, mass of bullet multiplied by velocity of bullet, will be equal to 0 because the speed is 0 since it wasn't moving initially. So this part will go, since anything you multiply by 0 give you a 0. So it means in the next step, we'll have just our MB, VB, this is 1, 1, is equal to, on the other side, we'll have everything we have there, which is MB2 and also VB2. That will be added to MB2 multiplied by VB2. So this is what we are going to have. On the left side, we'll only have the bullet, since it's the only one that has got a speed that is greater than 0. And then on the right side, we are going to have everything, because now this becomes a system. After the bullet has embedded into the block, this becomes a system, and they will be moving together. So now, that brings us to another manipulation of this formula, where we'll say MB1 VB1 will be equal to, now, since the bullet will go into the block and it becomes stuck there, it implies to say now the system will be moving together. The speed at which the block will be moving will be the same as the speed at which the bullet will be moving, since now the bullet is stuck inside the block. Since their speed will be equal, it means this speed here and this speed here will be the same. Speed for the block and the speed for the bullet will be the same. Since this speed will be the same, it implies to say we can call it, let's call that speed V. And we can factor it out there. It implies to say we can have that part as Z. Since the masses are different, we'll have the mass of the block here added to the mass of the bullet. Now, since the masses are not changing, we can just leave them as MB and MB there, and this will basically be multiplied by V, since V is the speed at which both will be moving at. So now this is the formula that will help us to find our V. The V we are looking for is this V here, so it will help us find that. Let me get rid of the top part so that we can use it. Let me put my formula on top there. So our formula now will be MB1 VB1 is equal to MB added to MB, that will be multiplied by V. Making V the subject of the formula there, what you'll get is, this is MB there. Making this V the subject, what we'll get is our V will be equal to MB1, then BB1 divided by MB added to MB, like that. So this is the formula that will help us find that speed. And when we replace here, we'll say the mass we have for the bullet is 0.05 kgs. And this will multiply by the speed that we have, which is 150 meters per second. Then this will divide by the mass we have for the bullet, for the block first, is 4.0 kgs. Then this will be added to 0.05 kgs that we have for the bullet. So now we need to do our mathematics here and find our speed. So when we do mathematics here, what we are going to find is, let's bring it here. So what we are going to find is we'll have on top there, according to my calculator here, I'm getting a 7.5. So I have a 7.5 kgs multiplied by meters per second, like that. And this will divide by, down here, I'm just getting a 4.05 kgs. And when we do our division here, what we are getting according to my calculator here, we are getting a speed of 1.85, 2 to 3 decimal places, and this will be in meters per second. The kg and the kg will go, the unit that will remain is meters per second, and this is the speed at which the system will be moving at. Now that we have the speed, we can go ahead and find the amplitude. So let's go ahead and find that. All right. So to find the amplitude, we can basically use the formula, which is Vmax is equal to angular frequency multiplied by amplitude. In this formula here, making A the subject, this will give us our A to be equal to Vmax divided by angular frequency. So using this formula can help us find our amplitude, but we need to first find the angular frequency. This is what we found there, ladies and gentlemen, is our Vmax. The speed at which the whole system will be moving after collision, that will be our Vmax. So we'll have our Vmax that we calculated already, which is 1.852. And then we'll just need our angular frequency, and that will help us find our amplitude. So let's quickly do that. We understand to say angular frequency can be calculated by the formula that says the square root of k over m. This angular frequency can be given by the square root of k is 500 newtons per meter, is given in the question, and our mass of the system, when you add 4 to 0.05, we are getting 4.05, and this is in the unit of kgs. So this one here, when we punch our calculators, let's see what we are getting. All right, so we're getting 11.111. It goes like that, so we can leave it as 11.11. So this is in the unit of radians per second. So this is our angular frequency. Now that we have our angular frequency, we can find our amplitude by just saying our amplitude will be equal to the Vmax that we got is 1.852. This is meters per second, and this will be divided by our angular frequency, which is 11.11 radians per second. All right. Then when we do our mathematics here, let me see what we are getting as amplitude. All right, so when we do that, what we are getting is 0.167. It's 0.166. It goes like that. So rounded off to 3 decimal places, we're getting 0.167 meters. So this is the amplitude that we're looking for. Now, this is one way we can find it. We can also use a different way. And let me quickly just show you another way we can find this amplitude. All right, so let's do that. So we can use another method, which is basically using the energy. Now, remember, after just collision, okay, just after collision, you find that at that point, which is the mean position, or the mean point, or the position of origin, just after collision, you find that that's the point where we have maximum velocity. Since at that point we have maximum velocity, it's the same point at which we have the maximum kinetic energy. At that point, what we have is the kinetic energy at its maximum, and that's the energy of the whole system. So kinetic energy is equal to the energy of the system at that point. So we can say at that point we only have kinetic energy, and then as it goes on the other side to a stoppage, as it moves and then it comes to a stoppage or it stops, what we are going to have now is the kinetic energy will be converted to potential energy. And the potential energy that we are going to have at maximum displacement there is basically equal to mechanical energy, which is energy of the system. So we can say kinetic energy at the beginning, at the end, will be equal to mechanical energy of the system. So we can use this to find our amplitude. Where kinetic energy is given by the formula, this is half mv squared, and mechanical energy is also given by the formula half k a squared, where k is the spring constant, a is amplitude. So since we have amplitude here, it can help us to find our amplitude. So let's write it properly. So that's a squared. Now we are looking for amplitude, so we're going to make it the subject of the formula. The first step is, since we have half here and half there, those two are going to cancel. When they cancel, what will remain is, so this and that will go. When that happens, what we have is now mv squared is equal to ka squared, like that. Then we're going to have, when we do mathematics, we're going to say our a squared will be equal to mv squared, that will be divided by k, like that. We divide by k there, and then our a will be equal to the square root of mv squared over k. All right. So this one now going to the other side will give us, since this v has a square there, on the v part, the square will cancel with the square root. So in other words, what we are going to have is our amplitude here will be equal to, let's take v out of the square root, since it has already cancelled its square and the square root, and this will multiply by, on the other side we'll have m, that is being divided by k. So our amplitude can be given by this formula, where we are saying A is equal to V. This V is the speed that we calculated, then multiplied by the square root of mass, which is the total mass, divided by the spring constant. So replacing here, you find that we have our V, which is 1 point. Let me do it on the other side. All right. So our formula is A is equal to V, the square root of, that was m over k, like that. Then replacing here, what we have is our V is 1.852, This will multiply by the square root of our mass is 4.05 divided by K, which is 500 here. All we have to do is punch our calculators. When we punch our calculators very well, we'll find that our amplitude is equal to 0.167 meters again. So you can choose any of the methods. It will still be okay. You're going to find the same answer, and this is how we go about it. Now, let's look at the second one, which is determine the fraction of the bullet's kinetic energy converted into simple harmonic motion. How do we solve this one? In order to solve this one, we need to calculate the kinetic energy at an initial point of the bullet and calculate the kinetic energy of the system. So let's start by finding the kinetic energy of the bullet here. So let's do that. Now, the kinetic energy of the bullet, let's say this is Ke of B. Let's just write bullet. This will be equal to 1 over 2 m, which is mass for the bullet, then V for the bullet squared. So kinetic energy of the bullet will be equal to half mb, which is mass for the bullet, then multiplied by speed of the bullet squared. So let's do that. We'll have 1 over 2 here. When we replace, the mass for the bullet is 0.05, and this will multiply by the speed that we have is 150, and this must be squared like that. So all we have to do here is punch our calculators. When we do that, what you are getting is we have 150 squared. This is giving us okay, multiplied by 0.05. That will multiply by 0.5. So this is giving me 562.5. So it's giving me 562.5 joules. So this is the kinetic energy of the bullet before collision. So let's save this value somewhere. Let me save it here. So kinetic energy of bullet is equal to 562.5 joules. So let's save it there and get rid of this part. Now the next step is to find the kinetic energy of the system after collision. So we'll say kinetic energy this time of the system is equal to, still we have half mv squared. Now this is mb added to mb multiplied by v squared. The v squared we're talking about is the speed that we calculated earlier on for the system. So this will be equal to 1 over 2. Now the mass of the block added to the mass of the bullet gave us a 4.05, and this 4.05 must multiply by the speed that we calculated, which is 1.852, and this is squared. So let's quickly do that. We have 1.852 squared. This multiplies by 4.05. and then it multiplies by 0.5. All right, so this is giving me 6. So this is equal to 6.995. So it is giving me 6.95 to 2 decimal places. So this is the kinetic energy of the system. This is the kinetic energy of the system. Now to find the fraction of kinetic energy converted into simple harmonic motion, we need to use the ratio that we have here. So we'll say, let me put it on the middle here. So the fraction that we're going to call F will be equal to the energy of the system, which is the kinetic energy of system, divided by the kinetic energy of bullet. So this is the ratio we're looking for. And this will be equal to, replacing with what we have. What we have is kinetic energy for the system is 6.95 joules divided by the kinetic energy that we have for the bullet is 562.5 joules. So all we have to do is do our mathematics there. And when we do that, let's say we have 1.6, that's not 6, but 9, 1.9, not 1, sorry for that, but 6. This is 6.95 divided by 562.5. All right, so this is giving me 0.01235. So this is giving me 0.01235. So I'll just say 124. So this is what we are getting. This is the fraction that is turning into kinetic energy of the system.